Limitations. Limitations of VSEPR theory. Limitations. 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 Limitations of VSEPR theory. Okay. Limitations of VSEPR theory. Okay. First point. VSEPR is not able to predict geometry of certain transitions metals complex. Okay. First point. VSEPR is not able to predict the geometry of certain transition metal complexes. VSEPR is not able to predict the geometry of certain transition metal complexes. Okay, VSEPR is not able to predict the geometry of certain transition metals complexes. Second point. This theory is not useful for predicting the shapes of molecules containing inert pair of electrons. Okay. Third point. This theory is not useful for predicting the shape of molecules containing inert pair of electrons. Okay. Next point. Okay. Third number. This theory is unable to explain the shapes of molecules having highly delocalized pi electrons. Okay. Fourth point. This theory cannot explain the shape of highly polar molecules. This theory cannot explain the shapes of highly polar molecules. Example, both lithium oxide and water should have similar structure. Example, Li2O and H2O should have similar structure. should have similar structure. Should have similar structure. Okay, should have similar structure. Valence electron is 8. Valence electrons 8, but lithium Li2, but Li2 is linear while H2O is angular, but Li2O linear, Hi2O linear, but Li2O linear and but Li2O linear and H2O and H2O is angular. H2O is angular. Okay, angular. H2O is angular. Okay, angular molecule. Angular molecule. Okay, having bond angle 104.5 degree. Okay, thus the shape and structure geometry of covalent molecules are determined by VSEPR theory and hybridization. Both are complementary to each other. With the help of hybridization and VSEPR theory, the structure and shape of the molecules of different types are determined. Okay, application of VSEPR theory. Application of VSEPR theory. Okay, 1 minute. Application of VSEPR theory. Application of VSEPR theory. Application of VSEPR theory. Okay, application of VSEPR theory. Limitation of application of VSEPR theory. Application of valence shell electron pair theory. Valence shell electron pair theory. VSEPR theory. Okay. First point. Point A. First point. Okay. Molecules having only bond pairs. Molecules having only bond pair. Okay, bond pair. The shape of the molecules is regular. Okay, molecular. The shape of the molecules is regular. The shape of the molecules is regular. Okay, the shape of molecule. The shape of molecules is regular. Molecules is regular. Okay, is regular. Okay. First point. AX2 type. Okay. AX2 type molecules having no lone pairs. AX2 type molecules having no lone pairs electrons on the central atom, because this is AX2 type 180 degree. Okay, AX2 type molecules having no lone pair electrons. AX2 type molecules having no lone pair electrons on the central atom. Okay, on the central atom. Okay, AX2 type molecules having no lone pair electrons on the central atom have regular geometry like linear. Okay, AX2 type molecules having no lone pair electron on the central atom having regular geometry like linear. In this type, two orbitals for the bond pair orbitals is needed. In this type, two orbitals for the bond pair orbitals is needed. So the hybridization of central atom sp and the structure as well as shape is linear. Okay, shape is linear. Example BeF2 BeCl2 CO2 etc. Okay, in BeCl2 the central atom is Be. It has two bonding electrons pair its outermost orbit. The bond pairs lie on the opposite sides of central atom Be, due to which minimum repulsion and maximum stability occurs. The bond angle is BeCl2 is 180 degree. Structure: this is Be and Cl 2 Cl2, and the structure is linear and angle is 180 degree. Bond angle is 180 degree. Okay. Second type. AX3 type. Okay. AX3 type. The structure AX3 type is a structure this is AX3 type structure. Okay, this is AX3 type structure. This is AX3 type structure. Okay, this is AX3 type structure. Okay, AX3 type structure. This is AX3 type structure. Okay, this is AX3 type. This AX3 type structure. Okay, AX3 type structure. AX3 type structure. This is a P sp2 and sp2 and P. The bond is sigma bond and fluorine. This is fluorine atom. The bond is sigma bond and this bond is sigma bond and P atom. This is fluorine. The structure is BE B F okay. In AX3 type of molecules having no lone pair of electrons on central atom A. This is central atom A. Okay, this is central atom A, okay? This is central atom A. This is central atom A, okay? And in AX3 type, this is X, this is X, 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 okay? Okay? In AX3 type of molecules having no lone pairs, of electrons on central atom A, have regular geometry like triangular planar. Three orbitals are needed for the bond pair electrons. Three orbitals needed for the bond pairs electrons. Three orbitals are needed for the bond pairs electrons. Hybridization is sp3. This is sp2. The hybridization is sp3 hybridization is sp3 hybridization, okay? And sp3 hybridization is sp3 hybridization, and the structure as well as shape is triangular, shape is a triangular, okay? Triangular planar. Example BF3, BCl3, BH3, etc. Okay, etc. In BF3 molecule, B is central atom. B is central atom. B is central atom has 3 valence electrons and is frames 3 sigma bond. It frames 3 sigma bond. Okay, with 3F. B has 3 valence electrons and its frames forms 3 sigma bond. It forms 3 sigma bond with 3 fluorine atoms. Okay, the 3 electron pair bonds lie at 120 degree. Lie at 120 degree. Okay, around central atom. The 3 electrons bond pairs lie at 120 degree central atom of boron. So BF3 molecules has triangular planar structure as there is no lone pair on the boron atom. So the shape is also trigonal planar. The bond angle is 120 degree because in this position bond pairs electrons lie apart from each other. So there is minimum repulsion and maximum stability takes place. Okay? Next application, molecules having only bond pairs in next application, application number third. Okay? 1 minute. Application number third. Application third, okay? Application third. AX4 type, okay? AX4 type. Structure is, this is A and this is X. This is X, this is X, and this is X, okay? This angle is 109°28'. Okay. AX 4 types. AX 4 types. The structure C H H H H. One 109°28'. Okay. Let's go. We will be knowing about AX4 type. Okay. AX4 type. Okay. AX4 type molecules having only bond pairs. AX4 type molecules having only bond pairs. Okay. And no lone pairs electrons present on atom A, and no lone pairs electrons present on atom A have regular geometry. In this case, 4 orbitals are needed. In this case, 4 orbitals are needed. So hybridization is sp3 hybridization. Hybridization is sp3 hybridization. Hybridization is sp3 hybridization. sp3 hybridization. Okay. sp3 hybridization. Okay. The structure and shape is tetrahedral. The structure and shape is tetrahedral. Tetrahedral. And the structure and shape is tetrahedral. Example, methane CH4. Example, methane CH4. Methane CH4. Okay. In methane molecules, carbon contains 4 valence electrons. Carbon contains 4 valence electrons which form covalent sigma bonds. Which form 4 covalent sigma bonds. 1, 2, 3, 4. Okay, 4 covalent sigma bond with 4 different atoms. Okay. Methane has CH4 has sp3 hybridization. sp3 hybridization as methane only contains bond, no any lone pairs. Hence, its structure as well as shape is tetrahedral. The bond angle is 109°28'. 109°28'. Okay. And next is AX5 type. AX5 type. Fourth number, AX5 type. AX5 type. Okay. AX5 type. Okay. Then this is phosphorus and this is chlorine and this is chlorine and this is chlorine. Okay. Chlorine 90°, 120°. Okay. Chlorine. AX3 type. AX5 type. AX5 type. Okay, in this type of molecules, the central atom has sp3 dehybridization, sp3 dehybridization. The structure and shape both are trigonal bipyramidal. Shape and structure both are trigonal, 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 bipyramidal, 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 bipyramidal. Okay, pyramidal. Example PCl5. Example PCl5. Okay, PF5. Okay. In PCl5, the central atom is phosphorus. In PCl5, the central atom is phosphorus. Phosphorus forms have covalent sigma bond with 5 different chlorine. 1, 2, 3, 4. 5 different chlorine with 5 different chlorine atoms. Hybridization in PCl5 is sp3. Hybridization in PCl5 is sp3. Hybridization in PCl5 is sp3. Hybridization in PCl5 is sp3d. sp3d. So the structure and shape is trigonal bipyramidal, and the 3 bonds angle are 120 degree. 3 bonds angle are 120 degree. 3 bonds angle. 3 bonds angles are 120 degree. Where is axial bond experiments 90 degree? Where is axial bonds experiments 90 degree? Axial bonds experiments 90 degree repulsions. Hence the 2 bonds angles becomes 90 degree. 2 bonds angles becomes 90 degree. Okay. And next fifth number, AX6 type. AX6 type. This type of hybridization contains only 6 bonded pairs and no lone pairs. As an example, sulfur. Okay. This is sulfur. This is sulfur and 4 chlorine. 1, 2, 3, 4. 4 fluorine atom. Okay. This is 4 fluorine atom. 1, 2, 3, 4, 5, 6. Okay. As AX6 type, this type of molecules contains only 6 bonded pairs and no lone pairs. 1, 2, 3, 4, 5, 6. Okay. This type of molecules contains only 6 bonded pairs and no lone pairs. Hybridization is sp3d2. sp3d2 has the shape and the structure both are same and octahedral. Okay, octahedral. The bond angle is 90 degree. The bond angle is 90 degree. The bond angle is 90 degree. Okay. Example: sulfur hexafluoride SF6. Sulfur hexafluoride SF6. Sulfur hexafluoride. In AX6 type, the bond angle is 90 degree and the structure is octahedral, and the hybridization is sp3d2 hybridization. As an example, SF6 sulfur hexafluoride. Next, 6 number. Okay, 1 minute. 6 number example. 6 number. Which 6 number? Okay. And 6 number is AX7 type. 7 type, AX7 type. 6 number is AX7 type, AX7 type. Okay. The structure is as example IF7 33617. Okay. This is iodine atom. This is iodine atom, and this is IF7 iodine octahedral fluoride. Okay. This is iodine atoms, and as like this figure is 1, 2, 3, 4 and 5. 1, 2, 3, 4, 5. 2 to 4, 5. Okay. 1, 2, 3, 4, 5, and this is 6. 1, 2, 3, 4, 5, 6. 2 to 4 to 6. 3, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. How to 1, 2, 3, 4, 5. Okay. And this next is a fluorine S7. Okay. And the structure is as like this. Okay. And the bond angle is 90 degree, 72 degree, and 72 degree. Okay. In AX7 type, IF7 is the typical example of this type hybridization. sp3d3 hybridization. sp3d3 hybridization. Okay. Hybridization. sp3d3 hybridization is sp3d3 in IF7. sp3d3 is in IF7. The shape and the structure both are pentagonal bipyramidal. Pentagonal bipyramidal. Okay. Bipyramidal. Total valence electron S in IF7 molecules. Total valence electrons S in IF7 molecules is 7 plus 7 multiply 7 equal to 56. Okay. And the number of octet is 7. Electrons used in octet formation. Electrons used in octet formation is 7 multiply 8 equal to 56. 7 multiply 8 equal to 56. Okay. And number of lone pairs is 0. And the orbital required is 7. Orbital required is 7, and hybridization of I is hybridization of I is sp3d3 structure, and the structure Structure is a pentagonal. Structure is pentagonal bipyramidal. Pentagonal bipyramidal. Okay. Structure is pentagonal bipyramidal. B type. Are in previous is A types and B is B types, and next is B types molecules containing bond pairs and lone pairs. In previous we will study about only lone bond pairs, and in B or in next we will be study about in molecules containing bond pairs and lone pairs both. Okay, the molecules containing bond pairs and lone pairs bond pair and lone pairs. Okay, molecule containing bond pairs and lone pairs, okay. The presence of one or more lone pairs causes some distortion in the geometry of molecules. The shape of molecules containing bond pairs as well as lone pairs of electrons are determined by valence shell electron theory, VSEPR theory, and hybridization. The shape of the molecules is irregular. The shape of a few important molecules and ions are discussed below. Okay? The presence of one or more lone pairs. Causes some distortion in the geometry of molecules. The shape of molecules containing bond pairs as well as lone pairs of electrons are determined by VSEPR theory and hybridizations. The shape of the molecules is irregular. The shape of a few important molecules and ions are discussed below. Okay? First, NH3 ammonia. Okay? NH3. In NH3, the central atom is nitrogen, and the electronic configuration of nitrogen is N7 is 1s2, 2s2, 2px1, 2py1, and 2pz1. Okay? 2pz1. In nitrogen atom has 3 unpaired electrons for bond formation. 3 unpaired electrons for bond formation. 1, 2, 3. 3 unpaired electrons in bond formation in ground state. But actually it is not found correct. Ammonia NH3 molecule is unsymmetrical, and X-ray analysis show that it is a pyramidal in shape, having bond angle 107.3 degree. Okay, and the structure is ammonia is a molecule, so unsymmetrical. X-ray analysis show that it is a pyramidal. It is pyramidal, and 1, 2s and 3, 2p. 1, 2s. Okay, 1, 2s and 3, 2p. 3, 2p of nitrogen atom hybridized to form of 4 sp3 hybrid orbitals. sp3 hybrid orbitals. 1 hybrid orbitals contains lone pairs. Hybrid orbitals, and 1 hybrid orbitals contains lone pairs, and the rest 3 hybrid orbitals contains 1 unpaired electrons. Okay, NH3 ammonia molecules is formed by the overlap of 3 sp3 hybrid orbitals of nitrogen atom with 3 hydrogen atoms containing 1 unpaired electron, 1s1. So the central atom nitrogen has 3 bonding electron pairs, 3 bonding electron pairs and 1 lone pairs Thus hybridization is sp3 hybridization due to presence of 4 needed orbitals. Structure of ammonia molecules is tetrahedral. This is the ammonia and 1 hydrogen, 2 hydrogen, 3 hydrogen and 1 lone pairs. Okay, 1 lone pairs. Okay, this is a ammonia, 1 lone pairs, nitrogen, 1 lone pairs, and this is hydrogen nitrogen bond, and the bond angle is 107 degree. As example, this is lone pair, this show the lone pairs, and this 1 hydrogen, 2 hydrogen, and this is a para 3 hydrogen. Okay, 1 hydrogen, 2 hydrogen, and this is 3 hydrogen. Okay, and 1 is lone pair. Okay, and thus the shape is pyramidal. Okay, this is structure and shape of ammonia molecules. Okay, so the central atom and nitrogen. So the central atoms nitrogen has 3 bonding electron pairs, bond pairs, and 1 lone pairs. Thus the hybridization sp3 hybridization due to presence of 4 needed orbitals. Structure of ammonia molecules is tetrahedral, but due to presence of 1 lone pairs of electron, its shape will be pyramidal. So the shape is tetrahedral, but due to presence of 1 lone pairs, the shape is also in pyramidal. A lone pairs occupies on 1 corner of a tetrahedron. A nitrogen atom is surrounded by bond pairs as well as lone pairs. According to VSEPR theory, the order of repulsion is as lone pair as is greater than lone pair, bond pair is greater than bond pair. Repulsion between these orbitals are not all of equal strength because all 4 orbitals are not in the same environment. The lone pair of electrons repel the other bond pairs strongly. Hence, the bond angle hydrogen reduced from 109 degree 28 minutes to 107.3 degrees in ammonia. Okay, thank you. Next is second is formation of water. Second is formation of water. Okay, 1 minute. Formation of water. Next is formation of water. 1 minute. Next, Next is formation of water. Second point, formation of water. Formation of water. Okay. Formation of water. H2O. Formation of water. H2O. Okay. H2O. In water molecules, oxygen is central atom. Oxygen is central atom. Oxygen is central atom. Oxygen is central atom. Okay. The electronic configuration of oxygen O6 O8 is given as a 1s2 2s2 2px2 2py1 2pz1 2pz1. Okay. And this is this is 2s2, and in p orbitals 1 2 1 2 3 1 2 3 4 4 to 6. Okay. And this is oxygen ground state. Oxygen in ground state. Oxygen in ground state. Oxygen in ground state. And one and 1 1 2 3 1 2 3 1 2 3, and this is 4, and this is a 2p4. Okay. This is a 2p4. This is 2p4. This is 2p4, and the hybridization is a 4sp3 hybrid orbitals of oxygen atom. 4sp3 hybrid hybrid orbitals of oxygen atom. Okay. And this is a 1 2, and this is a 1 2 3 4, and this is 5, and this is 6 H2O molecules. This is make a H2O molecule. And this hydrogen atom. This hydrogen atom, and sp3 hybridization. sp3 hybridization. Okay. A oxygen atom has 2 unpaired electrons. Oxygen atom has 2 unpaired electrons. 2 unpaired electrons for bond formation. 2s, and 3 2p orbitals hybridized to form 4sp3 hybrid orbitals. Out of these 4 hybrid orbitals, out of these 4 hybrid orbitals, 2 contain lone pairs. 2 contain lone pairs of electrons, and 2 have single unpaired electrons. The 2 half-filled sp3 hybrid orbitals overlap with 2 hydrogen atoms, 1s1, to form H2O molecules. 1s1 to form H2O molecules. Okay. These 4 hybrid orbitals are distributed tetrahedrally. As an example, this is oxygen atom, and 1 2 hydrogen atom, 2 hydrogen atom, and 2 lone pairs. Okay. This is 1, 2, 1, 2. This is 1, 2, 1, 2, and the lone pairs of electron. This is lone pairs of electron. Lone pairs of electron. Lone pair of electron. Lone pair of electron. Okay. Lone pair of electron and hydrogen bond structure tetrahedral. 1, 2, 1, 2, 3, 3, and this is lone pair. 1 minute. These 4 hybrid orbitals are distributed tetrahedrali. These 4 hybrid orbitals are distributed tetrahedrali. Okay. The two corners of the tetrahedral are occupied by 2 lone pairs. Okay. Occupied by 2 lone pairs. 1 minute. 1 minute, sir. 1 minute. Occupied by 2 lone pairs. Okay. The two corners of the tetrahedral are occupied by 2 lone pairs. The presence of 2 lone pairs distorts the normal tetrahedral bond angle of 109 degree 28 minute to 104 degree 104.5 degree. The shape of H2O molecules, water molecules, becomes a V shape or angular. This is because lone pair. This is because lone pair repulsion is greater than bond pair. So repulsion. The shape and structure of H2O molecules is given in this figure. You can also show this figure. Okay. Thank you. And next is third point. Okay. Third point. Structure and geometry of hybridization ion. Structure and geometry of hybridization ion. Okay. Structure and geometry. Of hydronium ion. Okay. Hydronium ion. In next lecture we will be studying about the structure and geometry of hydronium ion. Okay. Thank you. Application of particles in elastic position.